Very often, a reaction does not tell us the whole story. For instance, the reaction NO2 plus CO gives NO and CO2 does not involve a collision between NO2 and CO molecule. Now, based on the experimental data, this reaction is thought to occur in the following two steps. In step number 1, two molecules of NO2 are colliding to make NO and NO3, and in the step number 2, this NO3 reacting with CO to form NO2 and CO2. If you look at this final reaction, NO3 is not even there. So that means NO3 is appearing in step 1 and disappearing in step 2. So this is called a reaction intermediate that cancels out. If you will add these two steps, you will get the reaction. So molecularity, it is the proper term for how the molecules collide in a reaction. How the molecules collide in a reaction. Now, step 1 is bimolecular. Why? Because it involves the collision of two molecules. Step 2 is also bimolecular for the same reason. Unimolecular reactions involve only one molecule in the reactant. So, again, for the same reaction, NO2 plus CO gives NO plus CO2. Experimentally, the rate law was found as rate equals to K times NO2 raised to the power second. What does that mean? It shows in my final that the rate depends on the concentration of NO2 and not even CO, and it is a second order reaction with respect to NO. Now, but we know that the reaction is taking place in two steps. In step 1 is the slow step, and the slow step is considered as the rate determining step, and the fast step is not involved in determining the rate. Here, so if step 1 is the rate determining step, then if I will write down the rate equals K1, and there are two NO2 molecules, and let's say I'm writing it this, then looking at the rate determining step, if I write down the rate like this, then this theoretical rate law is in agreement with the experimental rate law. This supports but does not prove our mechanism. Look at this example. It's NO plus Br2 gives you NOBr, and experimentally determined rate law is rate equals K times second order with respect to NO and the first order with respect to Br2, and this is experimentally found rate law. These 2 and 1 has nothing to do with these coefficients. Now, the proposed mechanism for this reaction is step 1, where NO plus Br2 reacting to form NOBr2, and it's a reversible reaction, and step 2 is NOBr2 reacting with NO to form NOBr, and it's a slow step. There is an intermediate here, which is NOBr2. Look, that's not even in the reaction. So that means if there is an intermediate, that means an intermediate appears and then disappears. So our slow step is the rate determining step. So if I write down my rate based on this, it is K2 concentration times NOBr2 times NO. That's not my experimentally found rate. So, but I have to get rid of this NOBr2 because that's an intermediate that cannot be in my final rate law. So what I'm going to do, using the first step, I'm going to write down for the forward reaction, what is the rate? K1 times NOBr2. For the backward reaction, what is the rate? I have to, give me 1 second. This is, sorry, it is for the forward reaction, rate equals K1 times NO times Br2. For the backward reaction, rate equals K inverse 1 times NOBr2, because for the backward reaction now NOBr2 is a reactant. At equilibrium, forward reaction equals backward reaction, so I can say NOBr2 equals K1 NO times Br2. So I can find the value of NOBr2. Let's divide with this rate constant, get rid of this, and this is my NOBr2 value. I will plug this NOBr2 value here. This was from rate from the slow step. So what will the rate becomes? Rate equals K2 times NOBr2 now is K1 times K negative 1 NO. And can you see there is one more NO here, that will become squared Br2. And if you look, this rate, the theoretically found rate, matches the experimentally determined rate law. So that means this proposed mechanism for this reaction makes sense. I have one more question here to solve. So it says, consider the following steps, following multiple step reactions. And then here C plus D gives CD is fast, slow, CD2 gives this is fast, and this is an overall reaction. How do you get the overall reaction? By adding all the reactions. Based on this mechanism, determine the rate law for the overall reaction. So the rate determining step is your slow step, which is this one. So rate will be K times CD times D. Now this is my overall reaction, and in this overall reaction CD is not even there, so that means I have to get rid of CD. And how will I get rid of CD? By using, first I can use this reaction. So the forward reaction will be K1 times C times D. The backward reaction will be K inverse times CD. Forward equals backward at equilibrium, which will make it K1 times C times D equals CD. I can find the value of concentration of CD, and that is equal to this constant I can plug this value here, and then what will be my rate? K times, instead of CD I'm writing all this, C, D, and there is another D, and that makes it this. So my rate will be, all constants can be replaced with another constant. So for this reaction, the rate will be this.